Hello, thank you for attending this session. So, my name is Clement Escoffier. I come from France, so it's way too cold outside here for me. But in this session, I'm going to explain a little bit what reactive actually means and how Vertex, which is a project I'm contributing to, can help you to become reactive. Because in the last few years, everything became magically reactive. We have now Reactive Systems, Reactive Manifesto, Reactive Spring, Reactive Streams, Reactive Extensions, Reactive Programming, and so on. And all these different reactive are actually associated with different other concepts, like asynchronous, back pressure, spreadsheets, actors, events, and so on, data flow. So we will try to, in this first part of this presentation, we will try to explain a little bit what actually reactive means. So I'm a former academic. I spent a lot of time in university teaching and so on, and as an academic, I know almost nothing. But I can check in a thesaurus or in a dictionary what reactive means, and it's what I did when I started working on reactive. So I looked at the Oxford Dictionary. Here you have the URL. And I searched for reactive, and if you do it, even today, you will find this page here, saying that being reactive means showing a response to a stimulus. That's vague, but that's fine. There is a second definition that we have here, the second one, acting in response to a situation rather than creating and controlling it. This one is actually very interesting, and we will see why. So, if we take this definition and we apply it to software, we can say that a reactive software is a software reacting to stimuli such as message, request, metrics, availability, keystrokes, user inputs, failures. Wait. Does that mean that according to this definition, every software we have built since the 60s, 70s is reactive? Because the goal and the primary purpose of a software is to actually do what we ask him to do. To react to our user input, to react to the message it comes from internet and so on. And it's actually a little bit true. So the nature of software is to react. But so why reactive becomes such a thing in the last few years? We are going to see that. But before that, let's focus a little bit on this second definition. When we don't control things, when we don't create the situation, how do we write software? Because generally, when you write a software, you write the first lines, and you know, OK, when this line is done, it's just next line, it's the next line, and so on. So it's very sequential. But here, we don't control that. It's the definition. So can we really have a flow of control? Can we say this, or who is deciding what will be the next instruction your software is going to execute? Maybe it's just a comeback of asynchrony. Maybe your software is just now going to be controlled and to be executed according to the events, message, stimuli it receives. That actually looks simple like that. We will see that it's not that simple. But wait. So reactive become a big thing in the last few years. And if we look at the reactive landscape, there is three main areas. The first one is reactive systems. So reactive system has been defined by the Reactive Manifesto. I recommend you to read it. I will give the URL later. And reactive systems can be summarized as an architectural style to build distributed systems right. And believe me, I'm sure you are building a reactive system. Even a website is kind of reactive. It's kind of distributed. There is a second part, reactive programming. They more or less emerge at the same time, and they actually complement each other. So reactive programming is a paradigm to compose software, well, event-driven and asynchronous software. And the idea behind reactive programming is that your main construct is going to be a data stream. So a pipe in which you have items, and as soon as there is an item in the pipe, you can catch it, process it, and so on. And finally, we have reactive streams, because there is one issue with data flow and stuff like that. What happens if some part of your system cannot keep up? There is too many events. There is too many stuff. So generally, it just collapses or end up with an out of memory or data loss. And you can't do that. Reactive Streams is a complementary to a specification for reactive programming that provide an asynchronous and non-blocking back pressure. It's very, the specification is very simple, but implementing it, we do it in Vertex, it's very complicated. Fortunately for you, recent version of reactive programming libraries implement reactive streams, so you don't really have to manage it. It's done for you. So that's a little bit my story. Almost 15 years ago, maybe a little bit more now, I was software developer, and I was doing something very, very simple. I had user on one side, they was entering things in a very beautiful black and green UI, and these things were products, where they were, and then I was saving this in a database, and the user were able to do a very simple query on it, simple. So I was developing that, but pretty quickly, they asked me to say, well, you know, your code base starts to be a little bit too big, so let's extract this part and ask another team to maintain it. So for example, the pricing service, or something like that. So we did that. That was fun. My code base was reduced, and I have this service that was always running, or somehow, because sometimes I were updating it, and so on. And actually, we start realizing that everything started to be way slower. But well, we had to do it, so we did it. Obviously, we have the mirror interaction, meaning that my system and my nice UI can now be used by any software. So not through the UI, but through a new endpoint that we had to create and stuff like that. So it was before REST and so on, so it was callback and stuff like this. So we had to build such kind of things, and I was not really controlling how those softwares were made. And believe me, even if you write the best documentation you can and so on, they are able to get it wrong. So they correct me with wrong parameters and so on. So I had to fix a lot of things in my application to handle all those cases. Then, well, I quit this company, but the project continues. And what the next step was, our users start to be really, really picky. They don't want to refresh anymore. They don't want to have the information when they start the system and so on. They want to be notified as soon as one of the products they are monitoring change, or something like that. So a push notification. So this makes things a little bit more complicated, especially at that time, because we didn't have WebSockets. We didn't have all this stuff. So we need to find things with long polling and so on. Obviously, as everything started to be so complicated, we need a monitoring system. So we put some metrics and so on. We were sending that to this monitoring system, and everything was fine, except that all those interactions are actually remote interactions. Every time we are leaving the process space to go through the network, calling something different. And what we know about distributed system, it failed. There is no better definition of a distributed system. A distributed system is going to fail, eventually. You need to be prepared for that. And it failed for many reasons. So the reason that almost everybody understands is the reason on the right side. For example, the database can be slow. So we need to handle timeout and stuff like that. Or the services on which I'm relying on can be under update, can be dead, can be slow too, can react, or can behave not as expected and stuff like that. This part is also interesting too. You don't control when and how many users you will have at any time. At the beginning, it was simple. This system was used in France, and French people have a good thing during the night, they sleep. So at between 2 a.m. and 3 a.m., nobody was using my system. So I was able to update and stuff like that. This started to be a little bit more complicated when things like mobile and IoT emerged because they don't sleep. Damn it. So I cannot stop my system or restart my system at the middle of the night because this thingy first increases the traffic a lot and never sleep. So we need to find some way to do that. So basically what happens to this system very quickly, once we have all this stuff, that the monitoring was telling us that, yeah, you're going to die. You aren't going to collapse. There is too much stuff happening, and you need to find a different way of doing it. This is where we will introduce reactive systems. So reactive systems has been defined by the Reactive Manifesto. You have this URL here. And it's just an architectural style that infuse asynchrony and asynchronous message passing inside your system. And because you have this asynchronous message passing, you become elastic and resilient. And if you have become elastic and resilient, you become responsive. Let's have a look. So the first thing is that all my components are going to use message to interact. When I send a message, I don't send a message to a specific entity. I send a message to an address, a virtual address. I don't know. Maybe no one is listening to this address, but I don't care. I send this message. And on the other side, I have some other components that subscribe to this address and receive the message. Fine. So if I have lots of message, I don't really care because I can start another consumer subscribing to the same address, and then it will just dispatch among the set of available consumer. So this can be done using a round robin or something a bit more clever, but this is easy to achieve. When we have an error, when one of my consumers die or misbehave, so there is a couple of things that can happen here. Either the message go back to the sender, and the sender can decide what needs to be done in that case, or the message backbone say, oh, this message will not be hacked. I will send it automatically to another subscriber. So this is depending on your message backbone and what you want to build. Something also important is my producer who sends a message, when it expects a reply, and it may, it does not wait actively for this message. It doesn't wait in a synchronous way. It says, OK, I send this request, and when you're done, call me back. So that means that during that time, my system can continue processing and handling requests and sending other message. So, well, that's so simple, right? I can take my system and just put message all over the place, and everything is fine. We want to do that. That's simple. OK, I will just use send and addresses and stuff like that. And if you do that using traditional programming model, you get this. You get deadlocks. You get way too many threads. You get very, very complicated code because asynchrony means asynchronous code. And if you use threads for this, you are going to be in a lot of trouble very quickly. And believe me, this always happens in production, never on your development machine. So we need to introduce something a little bit different, what we call the asynchronous development model. So again, asynchronous development model is not something new. It's something that comes from the 60s. And the idea behind it is very simple. In the ideal world, like when you have 3 tasks to do, you start by 1, then you do the second one, and then you do the third one. Simple, that's fine. Fortunately, in the real world, you start the first task. Oh, man, I need to call this pricer service because I don't have the price. So you call this pricer service, and you wait for the response. Then you get the response, you continue your execution, then, oh, yeah, I need to log. I need to write something in the log. This is also blocking. So I write something in the log, and then when it's done, it's flushed and so on, I come back and I continue my execution, and so on and so on and so on. So in that case, if we apply this, which is the traditional way of building system today, if you want to handle 5,000 concurrent requests, well, we need 5,000 threads. Because most of the threads are going to wait. And what happens in microservices or in all systems where you have a lot of interaction with other peers and distributed peers. So the asynchronous execution model, again, it's not new, take another approach. Instead of having my big task like that, my task is divided in chunks. And as soon as the task cannot make progress anymore, it just releases the thread and say, yeah, OK, I have called this service. I will continue my execution when I got the answer. And as the thread is released, the system can, using the same thread, make progress on the task B, and when the task B cannot make progress anymore, does the same thing, then start task C, and so on, and so on, and so on. So it becomes very, very simple. If you need to handle 5,000 requests with this, you need a single thread. Because you will handle the first request. As soon as this first request cannot make progress anymore, it will handle the second request, and so on, and so on. So that's very, very efficient. But for this, you need three things. You need an asynchronous programming model. You need a non-blocking I/O library, bigger than just what the JVM is providing, something really big. And you need a task-based concurrency. And this is what Vertex is providing. So I told you that asynchrony and doing asynchronous code is not that simple. And let's have a look. In a regular world, synchronous and blocking, when you have a compute method, you do like this. Compute, you pass the parameters, and at the end you call your service, and then you return the result, and the caller is blocked until this result is returned. But you call it like that. In an asynchronous world, it's a bit more tricky. Generally, we have to pass a callback. And a callback will be a parameters of your method that will be called when the execution has been completed or failed. Because there is something we don't see here, is that compute can fail too. So we need a try-catch. We can't use try-catch in the asynchronous world because it's a callback thing. So we need to encapsulate the result and the error in a structure, which is this async result here. I'm using the Vertex API, but any asynchronous programming model will provide almost the same thing. And on the user side, you call compute, you pass a callback, here using Java 8 Lambda, and so on. So when we are in the synchronous world, my next execution, my next instruction is the next line. When I am in the asynchronous world, my next instruction is inside my callback. OK, fine. So if we do that, then we can quickly see how it can work for an HTTP server. For example, I create an HTTP server, and every time I get a request, I'm calling a request handler that gets this handler and do its stuff. So here, reactive hello, and so on. And every time I got a request, I'm calling this handler. So really task-based concurrency. Listen is also interesting here, because here we have an asynchronous operation, listen, so starting the HTTP server, take a lot of time because there is many things happening at the operating system level. Typically, it checks that the port is not already used. And as I always use the port 8080, there is a good chance that it failed for me, but let's see. So if I have the listen method, then I tell him, OK, start the HTTP server, tell me when it's done or whether or not it failed. So here, I need to do something like, if my result is a failure, do this, or, OK, I have my HTTP server. OK, I can do that. That looks relatively simple. Let's have another example. JDBC. Why not? In Vertex, we provide an asynchronous JDBC client. And in that case, every time that I need a SQL connection, I do client.get connection. I get an asynchronous result because I may run out of connection or the database may be dead. So I need to check if my result is a failure or not. And once I have my connection, cool. Then I want to execute my query. Obviously, this is asynchronous, so I need another callback, and blah, blah. And when I have done everything, then I need to close the connection, so to recycle it. So I have a third callback. So we have a callback inside a callback inside a callback. It's how Vertex is developed, actually. So, well, a lot of people like callbacks. It's relatively simple. It fixed one big issue of computer science today. When you write such kind of code, you don't have tab versus spaces war anymore. Because your indentation is 2 spaces, even 1. So no tabs. We fix it. We fix this issue thanks to callback. But yeah, callbacks, not easy to write, not easy to read. I like doing an experience of writing some callbacks-based code and 6 months later looking at it. It hurts a lot. So, and it's my code. So I can imagine if it's someone else's code or someone else read my code. Man, poor guy. So we need something else. And it's where we have reactive programming, because reactive programming, as I said, is the idea of composing event-driven and asynchronous software using data flow. Do we have Excel user here, or Google Spreadsheets, or whatever it's called, LibreOffice, StarOffice, or OpenOffice? Do we? Oh, yeah, a few of them. I do that too. Unfortunately, I do a lot of travel and stuff like that, so I need to do something that is very, very boring, my expense report. And before entering that in my lovely Oracle, I generally do it in Excel or in a Google Spreadsheet. So for example, when I do this, I have my expense report, say, OK, lunch, 15 euros, coffee, 25 euros, I need lots of coffee, drinks, 45 euros, I also need a lot of whiskeys, but yeah. And I compute the total and so on. If I do this in Excel or in any spreadsheet, this last cell is written this way. It's a sum of the other one. We all wrote that. That's really the 101 of Excel. So there is an observation here. That means that every time I change one of the value, this cell is updated, right? So basically, I enter a new value, for example, coffee, and then the total is updated. So it reacts. It reacts to that. So we need to understand this, that it actually creates not one cell, but a series of values. And every time that one of the observed cells is updated, we do that. We update this. So over time, we have a sequence of values. This is a stream. So now, with this in mind, you can know that your project manager or your manager that is spending his days in Excel and stuff like that is actually a reactive programmer. But they're not aware of it. Don't tell them. They will ask for a raise. OK, so how does that work? Imagine that I have this first stream, 1, 2, 3, 4, and so on. A stream can be bounded or unbounded. Imagine that I want to add +1 to all of this value. So I'm going to observe this first stream and do a +1. So the result of this is a stream. Because when I got 1, I emit 2. When I got 2, I emit 3. When I get 3, I emit 4, and so on. And then I have the blue one, the blue stream, that is going to observe the green stream and do some other computations that say, I take the 2 last value from the green stream and I do a sum, something like that. So if I want to write this in Java, that's not that simple. Fortunately, there is an API for this, which is named a Reactive Extension for Java. So it's an implementation of Reactive Extension, which is also an implementation of the Reactive Programming model. Reactive Extension for Java, RX, is very, very popular today, especially in the Android world, because they do a lot of asynchronous stuff. But it starts to really be almost everywhere. So in RX, a stream can have 2 names, flowable or observable. We are going to see the difference later. So for example, I can create a stream of integer with range, which will be all the integer from 1 to 10. 1 included, 10 excluded. Then I need my green stream is going to observe this stream. So here, ops. And I will map every of the items from the red stream and add +1. That's simple. So a map is a simple operation that takes each item and return an item, a modified item. So it's a synchronous operation, but you can extract, you can do plus, you can do a lot of things. The blue one is a bit more tricky. It observes the green one, we see here, and then it does 2 operations. One, create a window, so kind of a buffer of the last 2 value. OK, why not? And then use a flat map. So a lot of people are a bit afraid by flat map. What does that mean? Actually, I don't like this name. I generally explain it as a map and flat. So the first thing you will do, you will take all the values from the stream I'm observing and will apply an operation. But this operation is going to return a stream. And then we have the flattened part. It will take the stream and just flatten all the values in another stream. So it's like a map. You get all the values emitted by this map and just flatten them. There is one big thing, and you can be sure if you never use RX or if you never use any reactive programming, library, you are going to miss at the first time. So subscribe. Streams are lazy, really lazy. So that means that you can write and describe everything you did and everything you want to do, but if you don't tell him, oh, actually, I'm very interested by this. I really want to do it. It won't do it. And how do you say that? You just use subscribe. So subscribe will say, OK, now you materialize all this stream and you will execute all the operation. And subscribe here will get every value emitted by the green or by the blue one and just display them. So what's the relationship between this and what I was telling about taming the asynchronous beast? It's because we can use data stream to represent asynchronous operation. So remember my request, my HTTP server. This is a sequence of requests because I get one request, two requests, and so on. So I can map that very naturally as a stream of requests. It's what we have here. So as I said, in Eric Java 2, we have two ways, flowable and observable. In such kind of stream, we have three types of things that can be inside. We can have the value, so here my HTTP request, an error, which generally ends completely the stream, or a notification that I don't have any value anymore, so end of stream. OK. Then we have streams that are a bit more tricky. Single and maybe. They are streams, but of one item. But it's still a stream. So it's a pipe, and I can have only one item inside. In that case, you can have two notifications. Either I have the item or an error. The maybe type that has been introduced in Eric Java 2 is actually also interesting because it can tell you whether or not you didn't get a value. So this is typically interesting when you do a lookup by name or something like that. Give me the person with ID blah, blah, blah. It doesn't get any. This is not an error. This is just a maybe that will tell you that there is nothing here. Singles and maybe will be used for asynchronous operation. I'm calling a service. OK? This call is returning a single, and when I will get the reply or the response from the service, the single will emit its item, and I can continue my execution. Finally, we have completables. So completables are even weirder stream because they are a stream of no items. They will just tell you when it's done or if a failure happened. Very interesting when you do asynchronous method without value, well, return value, like a flush or something like that. So if we go back to my JDBC problem I had with nested callback, then I can write something like that. I want a SQL connection. This is an asynchronous operation I'm using, so I'm returning a single. Fine. Up. Then once I have this, I want to execute my query. So I use flatmap publisher, because there is a few flatmap flavors. I have my connection here. Then I meet my query. This is also an asynchronous operation. You see, in Vertex, we use this RX prefix here to tell you that it's going to be asynchronous. I execute my query, and then this is returning a stream of rows. So all my records or whatever. Then I will transform this stream of rows into a flowable. So that's what I do here. So now I have a stream, Eric Java 2 stream of rows. This is actually interesting here. When we reach the end of the stream, or if the stream failed, close the connection. So I don't have to do that in another callback. This returns, so this stream of row here, I just create a new product out of this here, and then I subscribe, and I have my set of products. So my callback inside a callback inside a callback with all the error management everywhere becomes this. If an error is thrown at any stage of this processing, actually subscribe as another version here with an error handler here, and will catch the error here in a single place. And as soon as an error is emitted by any stage, the rest of the processing is skipped. So it's actually very interesting and very easy to use. But there is an issue. What happens if one of my consumers is very, very lazy? So a French consumer. It happens a lot in France. So in that case, if I have data streams, Well, how does that keep up? So obviously, you can imagine, yeah, but if it's always called by the same thread, then the thread is blocked and so on. Yeah, except that we want to use asynchronous stuff. So we're not going necessarily to be called by the same thread. So we need to find different way of handling that. So for example, in my example here, this is going to crash. Because, well, to display this print stack trace, because I can't keep up with the number of elements coming in my stream. So we need solution for this. First solution, don't worry, we'll put a buffer. Everybody has this idea. So it's nice, you can handle small bumps, but yeah, once the buffer is full, what happened? We are back on the same situation. Either you create a very, very, very big buffer and you get a lot of memory, or you create a too small buffer, and then what happens when this buffer is full? So we need a different way. Obviously, you can say, when it's full, drop the data. I don't care. Is that acceptable? Imagine that I receive too many HTTP requests, and after 100, I discard the next 51. Probably not a good idea, not a good user experience. So sometimes it's acceptable, but most of the time it's not. So we need another way. Here we have Reactive Streams. So Reactive Streams is a protocol that will let the consumer to tell to the publisher when he's ready to receive data. So it's an inversion of control, because until now, I was pushing data. I had something observing me, and I was pushing this data. With Reactive Streams, it's a little bit different. But that makes a lot of sense, because now, if something becomes slow, it will tell its publisher to say, oh, stop. I need a nap. So this is actually interesting and very simple to use, because the subscriber here will observe the publisher, will get a subscription out of it, and this subscription will let him call request, saying, OK, I'm ready to handle X item, so 1, 2, 3, and so on. So the publisher will push in this number of items. If it has it immediately, if it doesn't have it, then when it gets it. When the subscriber is back on track and has finished processing those events, those items, it will remit another request, and so on, and so on, and so on. So very simple. So here comes the thing. Reactive Streams is a specification that has been defined a few years ago. It defined 4 types, very simple, but don't try to implement them. Because to get them right, it's very complicated. So prefer high-level API on top of that, like Apache Streams, Eric Java 2, or Reactors. They're all implementing Reactive Streams, and they all do the heavy lifting for you. Second interesting thing is that this IDE has been integrated in Java 9 under the Flow name. So it's not the same package name, so meaning that it doesn't compile if you want to switch to Java 9 Flow. So we need adapters there. So you need to be aware it exists. We have adapters for almost all of this library, but you need to be aware that you need to use it if you want to use Java 9 Flow. So let's back to our database access. What happens if one of my subscriber of my rows is too slow? Well, here I use flatmap publisher, and publisher is a reactive stream type. So it has back pressure, meaning that when this part here, or even map, become too slow, it will stop asking for new item. Say, OK, I don't ask for any item. When I'm back on track, I will do it. So here, for example, in Vertex, we have batch. So we batch the result. So it will work that way. You will get the first batch. And when the processing is almost done, it will ask for the second batch, and so on. So you are not overloading your memory. Because imagine you want to receive 1 million items. If you load 1 million items in your memory, and you have 5,000 users at the same time, then you are in a bit of a trouble. So by using RX here, we clearly say that, yeah, OK, I don't have to manage this subscription and so on. You actually can if you really want, but it's really to an expert level. So let me speak a little bit about Vertex and what we do in Vertex. In Vertex, we take a very different approach from what the other traditional frameworks are doing. we give you the freedom to do whatever you want. We let you shape your system as you want, and not as we decide you should do it. So it's really a toolkit. It's just a library. You put it in your Spring application, you put it in your JBoss application, you put it in your regular Java application, whatever. It has been designed since the first line of code with these reactive ideas in mind. I am reacting to message. So everything we provide is reactive. We have a set of asynchronous and non-blocking development models. You can use callback. We never know. Maybe you like them. You can use Rx. You can use Scala. You can use Kotlin with coroutines. You can use Groovy. You can use Ceylon, and so on. We provide all those language. When I say provide, it means that we provide the right constructs for this language. So for example, in Scala, we are using Scala futures because they are really well integrated into the language. With Kotlin, as I said, we use coroutines, and so on. We have a simplified execution model, task-based instead of thread-based. So we have one event loop. Well, a little bit more than this. We have one event loop by CPU cores. That means that I can do a little bit more things with just one event loop. The advantage of the event loop is that once you have been accessed by one event loop, you will be always accessed by the same event loop. Meaning, you don't need synchronized anymore. You don't need volatile. Anyway, who knows volatile? So it's always the same thread, so there is no concurrent access. It has a cluster message backbone that we call Evenbus, and it's used today in production in many, many systems. The advantage of Vertex is that you don't have to pick the flavor of reactive you need. We deliver the three things. It has been designed to build reactive systems. We support reactive streams, and we provide reactive programming using Eric Java 1, Eric Java 2, and other language. So let's reduce this application with Vertex. So everything is going to be asynchronous, and we are going to use message and stuff like that. So first part, I need to add my products inside my database. OK, so I have my database here. I'm using this insert method that returns a single, so a stream of one, when it's done with the inserted items. Why it's a single and not a completable? Because we have this ID generation, CINI, and stuff like that. So then in the subscribe method, I write my response, and so on. For the list side of it, the second type of action, I use my database, I do retrieve, I get a flowable of product, which is my POJO, and every time that I get one, I'm going to write it to my users. So here is the thing. If you want to collect all the data from the database and then flush it to the HTTP response, you may have trouble because of the memory, if you have lots of items. What I do here is that I'm using chunk request. So chunk request is not something new. It exists since HTTP 1.1. And chunk request means that I'm going to write my response chunk by chunk, so the name. So here what I do is say, OK, as soon as I have a product that comes back from the database, I'm writing it directly to my consumer. So I keep my memory very, very small. So now we have this scene here. I have extracted part of my code to a pricer service. So I need to call it. Let's use a web client or HTTP client for this, because it might be an HTTP URL. So here, I retrieve the data from the database, and for each of them, I need to call this service. So if I have 5,000 products coming back, I need to call it 5,000 times. That's a lot of I/O. But with Rx, I can do it like that. Database.retrieve. For every items P, I'm calling, here. Yeah. I'm calling my web client, which is an asynchronous HTTP client. That's my pricer, so I call it with the pricer. I'm sending the request. It returns me a JSON. I extract the JSON using map, and so on, and so on, and so on. And then I subscribe and continue doing the same thing. But if I do that, I'm breaking a little bit the idea behind reactive systems, because I'm calling a specific pricer. I have a URL. I know where it is. So maybe there is some kind of load balancer or something like that, like a Kubernetes service doing this. But maybe not. Maybe it's just one. And you don't want this, because if it failed, then your whole system collapses. Here comes the Evenbus. The Evenbus here will send almost the same thing. So it's the same API. If you look at that, it's web client become Vertex.Evenbus. And I'm sending this on this address here, pricer, regardless the number of subscribers to this address. So if one crash, I hope that there is another one that will handle the load and so on. And if I have two of them, it will just call 1, 1, 1, 1, 1, 1. The rest of the code is the same. So from HTTP to event, not much difference. So the last part. I need to call and to notify my users every time that I have a message or change in my products. So here we will reuse the Evenbus. And because the Evenbus is very simple in Vertex, there is something called bridges. And a bridge is just an endpoint that we open, and anything can interact with this bridge. For example, we have a SockJS bridge. So SockJS is not a very famous library, but it's very, very powerful. It manages a bidirectional interaction between a browser or a Node.js application and our Vertex application. It negotiates the channel it's going to use. So by default, it will try to use WebSockets and will degrade to server-sent events, long polling, blah, 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 blah. If you're still using Internet Explorer 6, it will still work because it will use an iframe. But I don't recommend you to use Internet Explorer 6 in 2018. But we never know. We still have customers using it. So if I have the bridge instantiated somewhere, the only thing I do is just say, OK, send this message on the Evenbus. It will be collected by the bridge, forwarded by a WebSocket or whatever has been negotiated with the browser to the user, and we're done. So doing this is one line of code. We'll skip that, and we will do the demo. So here is the full code of this. It's 100 line of code, all included, all asynchronous, single-threaded. I'm not sure I use the Evenbus. Oh, yeah, no, I do. So if I start this, and because Vertex is just a library, I can just write a main. Don't need anything else. So I don't need a plugin. I don't need anything. Done. It started. So now, if I go, where is my other browser? Here. If I do this, I have my products. OK, let's try to add a product there. Size this, and go to the terminal here. I need beacon. This? Yes, you see, it automatically appeared. Let's try from another browser. Safari, for example. If I redo the same, I move you here, and where is this? Now, in addition to bacon, what do we need? We need burgers. Done, on both sides. So what happened here is that I'm pushing a new product in my system. It calls the pricer service, gets the response, publish the event on the Evenbus. We have a SockJS bridge that forwards that using, in that case, 2 WebSockets to my 2 browsers almost at the same time. So we have built a complete system that was a complete nightmare in a few lines of code. No, where is my presentation? So the issue when you have many browsers and many, here it is. So all these reactive things, even if it's very, very old, has been designed for one thing, and it's popular today for one thing. It lets you build better system by embracing the asynchronous nature of the world around you. Everything we do is asynchronous. So reactive means you are building a software that is showing responses to a set of stimuli, whatever they are, metrics, failures, and so on. There is 3 main clusters in this reactive landscape. The first one is systems. It's actually what you probably want to build. A distributed system done right. Something that is robust, something that is responsive. But for this, you have many ways to build it, but you will see that pretty quickly it can become complicated. So you need the 2 complementary things, reactive programming for this Java-based, stream-based way of taming the asynchrony, and reactive streams, because if you don't use reactive streams, then the slowest part of your system is going to kill the rest of your system. And you don't want that. Definitely not. Vertex provides you all 3 of them. So you don't have to choose and so on, but the main idea behind it is that you are going to build reactive systems, and you can pick the other parts when you need them. That's it for now. Thank you. If you have any question, well, we still have a few minutes. If you are interested more about Vertex, microservices, and so on, we release these free books over there. It's available for free at this URL here. Don't worry, it's short. I wrote it, so it's very short. I'm French, so I'm lazy, remember. So it's only 70 pages, something like that. And if you have any follow-up question, you can contact me at this email address. This email address here. Thank you.
Thank you. As Clement said, there was time for questions here. Any quick question? Yeah.
I forgot to say, I have Vertex stickers if you want some.
One question is, I haven't seen in the demo any tests for the framework, and how do you test these kinds of clients?
Do you really need tests? Aren't you confident in your code? Oh, come on. So no, well, it's actually a very good question, because if you use JUnit, the test stops when, well, it's considered as successful as soon as it exits the test method. Fortunately, because it's asynchronous, when you reach the last line of your test, it may not be done. So in Vertex, we provide several ways of doing this. We have something called Vertex Unit, which lets you write unit tests, asynchronous unit tests using JUnit, ArmCrest, AssertJ, or whatever assertion library you want. For JUnit 5, we have done a JUnit 5 extension. Same thing, the same idea of being able to write asynchronous tests. Every Java 2 comes also with a cool set of testing features, especially if you do things with time, like give me the create a windows of the on 1 minute, all the events on 1 minute, something like that. You don't want to test to spend 1 minute, so they can fast forward the time, which is a pretty good idea. Reactor is doing the same thing. So we provide libraries and features to let you test your application. Especially in the asynchronous way, you cannot be really confident. Any other question? Yep.
How about long-lasting JDB queries, like that if you have to fetch a lot of data and it took
very long
20 minutes to fetch it, and you get about 370 million rows?
So there is 2 questions here. The first one is, how do you integrate synchronous call and blocking call in an asynchronous application? And it's a very good thing, because it's the limit of reactive. Today, if you really want to be fully reactive, everything needs to follow this idea. Unfortunately, we need to be pragmatic. And most of the libraries and so on are still synchronous and blocking. In Vertex, we provide several ways of doing this by offloading the work to a worker thread pool or to a set of worker thread pool. Be aware that even if it works, you should avoid it or use it with precaution, because tuning a thread pool is like predicting the futures. It's very hard. Then, in your case, if you have a lot of data, and this data cannot be batched, because most of the time we can say, OK, give me the 20 first, then the 20 next one, and so on. So yes, I get everything on the it takes 20 minutes to get everything, but I could have processed the beginning immediately. In that case, you need to be aware that do you have enough memory? That's the first thing, to collect everything. If you do, well, these blocking abilities will be used for this. If it takes 20 minutes, you also need to be aware that your UI and your user experience need to be adapted for this. Don't create a spinner for 20 minutes, because this is very, very boring. And after a few seconds, I will just refresh, which will remit the same query, and I'm going to kill something. So yeah, when you have blocking things, we provide constructs. It's not perfect, but at least it's pragmatic, and we do it a lot.